Are you recording? Yeah, okay. We are good to go. Okay, let's begin this morning session. And the first speaker is Nishimura, and he's going to tell us about quantum tunneling in the real-time path integral by the Lefschetz thimble method. I hand over to you, John.
Okay, thank you. Thank you, Tenjo. First of all, as one of the organizers, I would like to thank all of you to participate in this workshop. And I'm very sorry that I cannot be in Corfu this year, but hopefully next time. So the topics I'm going to discuss today is largely motivated by the work I'm doing about IKKT model, namely the simulations, because we really need to have some good method to study IKKT model, and the reason will be clear soon. But this talk is based on something, is quite, unrelated to IKKT model. It's about quantum tunneling. And this work is done in collaboration with Katsuta Sakai, and who is a postdoc in KK, and Atis Yoskrapov, who has been my student, but he got the assistant professorship in Niigata University. Okay, so let me start. Oops, here it comes. Okay, so first of all, quantum tunneling is usually described by instantons in the imaginary time path integral. And as you know, decay rate of a false vacuum in quantum field theory has been calculated for the first time by Coleman in 1977. And quantum tunneling is also relevant in bubble nucleation in first order phase transitions and domain wall fusion and so on and so forth. So it's very important in quantum field theory. So typically what you will do, so let me use my pointer, is you start from this real-time path integral, but with this Lagrangian, where we have this double well potential. So this is basically the quantum tunneling, but in order to study this phenomenon, what you do usually is to make a weak rotation to imaginary time, and you end up with this partition function with this action in the Euclidean formalism, where you have this potential term flipped compared to the Minkowski one. So you have this upside down potential for the double well, and there you consider a classical motion starting from one of the hills here and then going to the other one. That corresponds to quantum tunneling in the Euclidean picture. And the classical solution is given by tangent hyperbolic, as you know, in this particular case. And then that is called instanton. And then basically tunneling amplitudes can be calculated within the semi-classical approximation using this instanton solution, and it is given by this instanton action S0, which is finite. And this is a non-perturbative phenomenon in particular, because if you want to expand this amplitude with respect to h bar, you get basically 0 to all orders. So this is purely non-perturbative phenomenon. Now, the question I would like to ask in this talk is, how can we deal with this quantum tunneling directly in the real-time path integral? That is the question. And sorry, yeah. I just want to get okay, sir. And the motivation for that is, first, in reality, there are also contributions from classical motion over the barrier, which is typically represented by Sphaleron configurations in quantum field theory. So just calculating instanton contribution may not be sufficient in some cases. And another motivation is to obtain the wave function after tunneling and its subsequent time evolution. For that, instanton calculation is not powerful enough. And we really need to solve the real-time path integral problems. However, as I will discuss shortly, a naive analytic continuation of instantons leads to singular complex trajectories, as has been pointed out for the first time by Sherman and Unzel some years ago. And we are going to clarify this issue completely by explicit Monte Carlo calculations. That's the aim of this talk. Okay. I have some problem in going to the next page, but maybe I should stop using this pointer. Okay, this seems to help. Okay, now, so the basic idea of Monte Carlo calculation is the following. If you have a path integral like this with this W, well, used as the weight, then observables can be calculated by generating configurations X with this probability if W, this weight, is positive definite. And then you can calculate the expectation value of O as the expectation values of O in this, for this probability distribution. That is the basic idea of Monte Carlo calculations. However, for the problem we have, namely the real-time evolution of the wave function is given by this formula, where the weight here is not positive definite, but rather complex. In particular, due to, well, first of all, the initial wave function and also this phase factor. So you cannot really identify this weight as the probability distribution, and that is called the sign problem. And there are many promising methods to tackle this problem. In the IKKT model, we have the same problem, and the next speaker is going to talk about complex advanced simulations of IKKT in this context. But today in this talk, I would like to use a different method, namely the Lefschetz thimble method, to overcome this problem for various reasons. Okay, so the plan of my talk is the following. I first review previous works on quantum tunneling, Sherman and Unzel, and so on. And then I discuss the method we use. And then I explain some recent developments of this method due to our research, namely backpropagation and optimizing the flow. And then I will discuss our results of these simulations, which clarify how quantum tunneling can be described in the real-time path integral. And then I will summarize. Okay, so let us first discuss the previous results by Sherman and Unzel. So let us consider this case with this double well potential. And as I said already, we make a weak rotation with this phase factor alpha. And then the Lagrangian, this Lagrangian will become this one after this phase rotation of the time. And at alpha equals pi over 2, you get imaginary time. And that is basically the Euclidean formulation. And in that case, you have the solution to this, to the equation of motion, which is given by tangent hyperbolic, as I explained already. But now, if you leave this alpha arbitrary, then you find that the same classical solution, well, can be obtained by in this way with alpha introduced in as the phase. So this is the classical solution for general alpha after the weak rotation to some alpha. Okay, so as I said, at alpha equals pi half, you get this instanton solution. And if you draw this, well, this is basically x versus time, Euclidean time tau. But if you draw this instanton solution in the complex plane of x, then since this solution is real, you have just a line on the real axis. However, if you now try to consider approaching alpha equals 0, which is real time, then something strange happens. At alpha equals pi over 8, you have this imaginary part already. And if you draw this on the complex plane of x, you have this funny spiral motion. And if you go even to smaller alpha, you get this picture. where you have highly oscillating behaviors for both in real part and imaginary part. And if you draw this on the complex plane, you have infinitely many spirals going on, and then you go into this well, and again, there are a lot of spirals. And this is for 10 to the minus 2 values of alpha, but if you take alpha to 0 limit, this becomes singular. So after all, in this paper, they don't find what kind of path is really responsible for quantum tunneling. And another important work is done at the same time, Koike and Tanizaki, and they discussed the solution in the double well potential, exact solution. And they started from the conservation of energy equation like this, and they find that there is a analytic solution to this equation given by Jacobi elliptic function, where this form includes two integration constants C and P. And these two integration constants can be determined by boundary conditions that you impose at both ends of the time, like -1 and 1, corresponding to the bottom of the double well. However, there are still infinitely many solutions labeled by integers n and m. And in particular, when either n or m is real, you get all these real solutions. This is quite natural because you just start from one of the well and end up at the other well. And in this case, you go further to the right and then go back to the bottom. And in this case, you have oscillation. So there are a bunch of, infinitely many real solutions like this. But on top of that, they also find complex solutions, which correspond to both n and m being non-zero. And in that case, you have this imaginary part and also highly oscillating behaviors as you go to larger and larger labels, n and m. And in particular, they point out that the real part of the action becomes finite as you go to larger and larger time difference. In these plots, they took t equals 10, but if you go to larger t, typically for finite n and m, you get real part of the action being close to 0. But if you make the labels large enough, then in the long time limit, the real part of the action becomes finite, which means that you have this typical instanton suppression factor. So they speculated in their paper that, probably the complex solutions with large integers n and m are responsible for quantum tunneling, but that means that highly oscillating trajectories are responsible, so it's very hard to study in reality. But, what we find is totally different from what they conjectured, so let's see. So before discussing our results, let me first explain the method, because this problem is in fact very difficult to study due to the sign problem, and we have to develop our method. So what is Lefschetz thimble method? For that, let us consider a general model defined by a multivariable integral like this, where x represent n real variables, and action here is complex valued. And the observables are given in this way, but it is difficult to evaluate due to the sign problem. Now, the general thimble method was proposed by these people, and the idea is the following. So this is the original integration contour, and starting from each point on the original integration contour, you solve some differential equation to obtain some points in the complex plane. And that way you can define the deformed integration contour. And when the flow time becomes infinite, you approach the Lefschetz symbol. That is basically their method. And I'm going to tell you what is the flow in the next slide. And you will see that as a result of the property of the holomorphic gradient flow that we use to deform the integration contour, the sign problem becomes milder on the deformed contour, and that is the idea. So this is the holomorphic gradient flow. It is a differential equation with respect to this complex valued variables z, and the derivative with respect to the flow time sigma is given by this, basically the derivative of the action with respect to this z, the variables, dynamical variables. And we solve this differential equation from flow time sigma equals 0 to some value tau, so that at finite tau, you get some integration contour like this. And if you send tau to infinity, you get something like this, which is the Lefschetz thimble. And so this flow equation gives you a one-to-one map from some real value x on the real axis to z of x and tau. And what is the reason for using this holomorphic gradient flow to deform the contour? The reason is very simple. It's just given by these three lines of equations. Basically, you have to take the derivative of the action, which is complex in general, with respect to the flow time and see what happens. And then using the chain rule, you get this. And then since this part is given by this part, this right-hand side, due to the definition of the flow, you get just the absolute value squared of the derivative of the action, which is real positive. So notice here that we are considering a derivative of some complex valued action, and then we get real positive. So this means that the real part of the action increases along the flow, while the imaginary part of the action is kept constant. That is the most important property of this holomorphic gradient flow, and that is precisely the reason why the sign problem becomes milder on the deformed contour, because typically what happens is that if you start from some point on the real axis, the real part of the action grows infinitely large, and then they flow away. And the only exception that happens actually if you're going to flow into the fixed point, which is given by this equation. So in that case, the right-hand side of the holomorphic gradient flow is 0 for the fixed point. So you will just stop there. That is the meaning of fixed point. So in that case, the real part of the action will not increase to infinity, but it just approach the value at the fixed point. So that is the exception, the only exception that you can get finite real part of the action, and otherwise you have infinitely large real part of the action, and then because of the Boltzmann weight, all such configuration will be irrelevant to the path integral. So in fact, on this real axis, the configurations that contribute to the path integral after deforming the contour is very limited. So only a very small part, only small part of the region on the real axis will contribute to the integral, and therefore within that small region, the imaginary part of the action will be almost constant, and that is the idea. And in particular, when you take the large tau limit, you get the thimble, Lefschetz thimble, and on this thimble, imaginary part of the action is constant. Basically, the sign problem is optimally reduced. Okay, and now using the Cauchy's theorem, starting from the original partition function, you can deform the integration contour like this, and then you can also parameterize the integration contour by the real values on the real axis. So this is just a parameterization of the integration contour by x. So please don't confuse this with the first line. This is totally different from the first line, but it is rather equivalent to this one. And then you have to take into account the Jacobian for the change of variables from z to x. And well, so these are the formulas that you are going to use when you apply the Lefschetz thimble approach. And so in particular, when you calculate some observable expectation values of it, you have to use this reweighting formula where this theta includes not only the marginal part of the action, but also the phase of the Jacobian that appears here. Okay, so that's the idea. And the problem of this generalized Lefschetz thimble method is, first, one has to solve the homomorphic gradient flow to sample each point on the deformed contour. That is quite demanding when you do it numerically. And in particular, the Jacobian you have to calculate when you do the reweighting, and that is also time consuming. In fact, that is the most time consuming part in this calculation. And another problem is when there are more than one thimbles, the tunneling from one thimble region to another does not occur very frequently if your tau is large, too large, and that will cause the ergodicity problem. So in this figure, I only have one thimble that contributes to the integral, but if you, in principle, you can have many more thimbles, and in that case, those thimbles are typically disconnected to each other, so there is no way to go from one thimble to another if your tau is large enough. But these two problems has been overcome recently by Fukuma's group. This first one was overcome by using hybrid Monte Carlo algorithm, and the second problem of ergodicity was overcome by using integration over the flow time technique. I'm going to discuss briefly in the next section. And now recently we have proposed something new in this context, namely the use of backpropagation when we do hybrid Monte Carlo algorithm in this method. So now let me explain. So when you apply this contour deformation, as I explained already, there are two possibilities for hybrid Monte Carlo algorithm. Namely, if you use this formula 1, you're basically proposing new configurations along this deformed contour and choose the new configuration by using Hamiltonian equation with the force given by the derivative of the action, the real part of the action on this contour. That is one possibility, but the other possibility is to use the equation 2, where you do hybrid Monte Carlo on the real axis, and you propose a new configuration represented by x, and then calculate the force of the real part of the action as a function of x. That is another possibility. And these two are, of course, well, you might say that these two are equivalent, but yeah, of course, mathematically equivalent, but there are some, well, practical differences. So here I summarize the differences. So the first one, namely the hybrid Monte Carlo algorithm on the deformed contour, is proposed by these people. And in that case, you have to solve the Hamiltonian dynamics on this deformed contour, which is very cumbersome because you don't know what is the deformed integration contour a priori. So for that, you have to solve the flow equation every time you make a new step on this line, on this curve. And on the other hand, when you calculate the force in the Hamiltonian dynamics, that is given by this formula. So it is very simple. So it is quite straightforward to calculate the force. And in this calculation, since you use this formula, determinant J is already included in this volume factor. So you don't have to, well, basically this Jacobian factor is included in the measure. That is the kind of advantage of this method. On the other hand, if you're doing hybrid Monte Carlo on the real axis, then the Hamiltonian dynamics is unconstrained because it's just on the real axis without any constraints. So Hamiltonian dynamics is straightforward, But the force calculation seems to be slightly more complicated than this, because you have to take the derivative of the real part of the action with respect to x, whereas the action is given as a function of z, right? So this was the bottleneck in the second approach, but we propose to use the idea of backpropagation, which is commonly used in machine learning. So that is kind of a breakthrough in this second approach. And however, the problem is that the Jacobian has to be reweighted because it appears in this expression. So that is the kind of a drawback of this approach. And in particular, if you have this factor in the reweighting, that might, in principle, cause the so-called overlap problem, and that is kind of worrisome. But recently, in our collaboration, we find a way out of this problem, namely how to overcome this overall problem. And basically, we propose to improve the flow equation. So let me briefly explain the idea. So the problem of divergence of the flow equation is the following. As I said, this is related to the mechanism of how the sign problem is solved in the thimble method. As I said, very small region on the real axis is basically exponentially expanded with the flow equation. And that's why on the deformed contour, the sign problem becomes mild. The imaginary part of the action does not fluctuate much. That is the idea. However, this also means that you have an exponential expansion of small region to large region by the flow. And in particular, the problem is that the expansion rate depends on the fluctuation mode, as I show in the next slide. So let us consider two examples of the flow. So Z of sigma and Z tilde of sigma, which is represented by these two blue lines. And then we consider the infinitesimal difference of these two flows and see how this difference will grow with the flow time. Now, Z and Z tilde satisfies this flow equation, and therefore the difference should satisfy this equation, you can easily see. And this H is the Hessian, namely the second derivative of the action. So you have this Hessian acting on the right-hand side. And clearly this means that the expansion rate is represented by the singular values of this Hessian H. So if you have many modes and if the singular values have a large hierarchy, then the expansion rate can depend on the mode a lot, and that causes a problem. So singular value is basically the decomposition of this matrix in terms of unitary matrices and lambda, which is diagonal. And you can order the singular values in this way, and that is the definition. So if you decompose this Hessian using this singular value decomposition like this, typically you have this lambda, which has a huge hierarchy. And let us call this condition number, which is defined by the largest singular value and the smallest singular value. And if the condition number is huge, then the expansion rates will have a huge hierarchy. And of course, in order to solve the sign problem, the flow time should be large enough, but you have to use the flow time, which is much larger than 1 over lambda n, which is the smallest singular value. But then the largest singular value mode will have this expansion rate, lambda 1. So typically, if you flow the equation for some time, tau, then this becomes huge. And that makes the flow diverge. But, well, in fact, there is a way to improve the flow equation. Namely, we can have some matrix A acting on the right-hand side of the flow equation. And using this degrees of freedom, we can somehow solve this problem of hierarchy completely. That's what I would like to point out. But of course, you cannot have arbitrary matrix here because you have to maintain the crucial property of the flow, which is basically the derivative of the action with respect to the flow time should be real positive. And for that purpose, this A should be basically Hermitian positive. So it has to be Hermitian, and moreover, it has to have all the eigenvalues being positive. So that is the only constraint, to have this crucial property. But using that degrees of freedom, we can actually choose this A in such a way that the expansion rate becomes all equal. It's just a simple calculation like this. And after using this A, basically the flow equation for the difference of the flows will have no matrix with large singular values hierarchy. Okay, so now for the rest of the time, I would like to discuss our results of for the quantum tunneling program. That turns out to be very interesting. And so the program we are considering here is given by this partition function, let's say. So we have this integration over all the paths connecting the initial point and the final point. But for the initial point, we have this wave function. So this is the initial wave function that we prepare. And then we have this action. And everything is in the real-time formulation. So this is not Euclidean anymore. And therefore, we have this I in front of the action. So if you're going to apply the conventional Monte Carlo idea, this is a horrible thing to do, and you can never get any answer. But now we are going to use the thimble method, and I'm going to show you some results. Okay, and the action is given in this way with the kinetic term and the potential term with minus because we are in the real time. And the potential is given like this. It has two double well like this at -1 and 1. And the initial wave function is chosen to be like this. So basically it's Gaussian and centered at x equals 1, which is one of the potential minimum. And okay, thank you. Then we discretize time like this. So we have t as a time from ti to tf, but we discretize it by n sections, and n is chosen to be 20 and t is 2 in the following. Now these are the results with the optimal flow. So these are typical configurations at large tau. So these solid line represent our numerical results, and this dashed line are taken from Koike Tanizaki with the initial value being complex. So that is the crucial difference between Koike and Tanizaki. In their discussion, they fix their initial point to be real at -1 and 1, because those are the potential minima. But in our calculation, since we have this initial wave function in the partition function, the point x at ti, the initial time, does not have to be on this potential minimum, but it can be flowed into complex values because we are using the Lefschetz symbol approach. And that's why this point here is in the complex plane rather than at x equals 1. And therefore, we have to solve the classical equation motion in Koike Tanizaki with this boundary condition, which makes the solution complex like this. And we have a very good agreement with one of the solution, which is labeled by 1, 0. And this is another typical trajectory we obtain from simulation, which is similar to 2, 0 solution of Koike Tanizaki. So if you fix this point to the real value like x equals 1, then you get real trajectory as Koike Tanizaki pointed out. But if you move away from the real axis, then it becomes complex, and those complex solutions seem to explain our numerical results. And if you take an average over all these trajectories, you get the expectation value. And that corresponds to the so-called weak value of the trajectory defined in this way using the operator formalism. So this has a very clear physical meaning, namely the expectation value of this x of t that you obtain by simulation has a clear physical meaning. And the result is plotted here with these symbols, and the dashed line is the result for this calculation based on solving the Schrödinger equation. So we just solve the Schrödinger equation to obtain the time evolution of this initial wave function. We multiply x and then solve the Schrödinger equation once again and take the inner product with this and the ket state. And that way you can obtain the basically the expectation value of the complex trajectories analytically, and they agree very well. So we are very much confident with our results. And moreover, it has a very clear interpretation, namely quantum tunneling is indeed represented by complex trajectories. And this note that these complex trajectories are not the ones speculated by Koike Tanizaki, because first of all, n and m are not large, and moreover, one of them is zero, meaning that in their language, they are real trajectories, not complex. So they are complex just because the endpoint becomes complex. And now we can also introduce some momentum p in the initial wave function and see what happens. These are the results. We obtain these solid lines, which can be compared with this dashed line, which is the solution of Koike Tanizaki labeled by 1, 0, this one for 2, 0. But the point here is that this endpoint becomes closer to the real axis. And as I explained, Koike Tanizaki's solutions becomes real if the endpoint is real. So that's why the trajectories, all the trajectories come closer to the real axis. And if you take the average, you get this result. But this also has a very clear physical meaning, because if you introduce momentum in the initial wave function, then you can easily go over the barrier by classical motion. And therefore, you don't need quantum tunneling to arrive at the other well. And that is precisely the reason why you get almost real trajectories in this case. So these are just typical examples of our results, but we can do a lot of experiments that will be very useful to understand the quantum tunneling from first principle. So let me just briefly explain the relationship to the previous works. So the difference from the previous point is that we are inserting some initial wave function, but in their case, they fixed the endpoints x equals 1 and x equals -1 to be the final and end point of their trajectory. And that is why they got these funny spiral behaviors. And so, but after introducing this wave function, we can still send this width of the wave function sigma to be smaller and smaller and see what happens. In that way, we can see whether our results approach what they are claiming. And these are the results for sigma equals 0.2, 0.15, and 1.2. As you decrease sigma, indeed, we have more and more complex-like trajectories. And moreover, in their case, they have long time limit. So we have to also take this time to be larger. And then we have more and more chaotic behaviors, which looks similar to what Sherman and Unzel first found in their papers. So, well, this is still under investigations, and we don't have complete answer, but I think our results are consistent with what Sherman and Unzel was claiming. So let me summarize. So as I explained, quantum tunneling, the real-time path integral has important applications in quantum field theory and quantum cosmology and so on. And unlike the previous work, we performed explicit Monte Carlo calculations for the first time, I would say, based on the Lefschetz symbol method. And by introducing the initial wave function, we found complex trajectories are responsible for quantum tunneling. And also introducing momentum makes the trajectories closer to real, which can be understood quite reasonably. And on the technical side, I would like to emphasize that we have used hybrid Monte Carlo calculations on the real axis as opposed to the one on the deformed contour as that Fukuma's group has been proposing. And in that case, the calculation of the force was done by backpropagation, which is very important. And also we found that optimizing the flow is important as well. And so far, we don't see any overlap problem due to reweighting of the Jacobian in this approach. So I think this approach is at least comparable to what Fukuma's group are proposing. And finally, well, the hidden motivation of this work is to apply this method to, let's say, finite density QCD or even IKKT model in the near future, because so far we have been using complex Langevin method, but that method has some validity criterion, and sometimes in some parameter region, that validity criterion is not satisfied. In that case, the complex Langevin method does not work. And well, since this Lefschetz thimble method does not have such restrictions, so we hope that this method is more flexible and has a larger region of validity. So that is my hidden motivation. But anyway, I hope we have found something very interesting and hope to discuss with you if you have any questions. Thank you.
Excellent, thanks. And for questions.
So in your diagram, you had one Lefschetz thimble. And so my question is, when do you have one or more than one Lefschetz thimble?
I see. Yes, typically there are more than one Lefschetz thimble. And for instance, in the case of this real-time path integral, as I said, there are infinitely many fixed points. And in principle, all these fixed points should contribute, but depending on the initial wave function or depending on the potential or the parameters like the duration of time and so on, there are some dominant fixed point and less dominant fixed points. So in practice, we don't have to sum over all those fixed points, but yeah, that is the situation. Typically, we have many thimbles contributing.
Sachin.
I wanted to ask you if you can include fermions in your discussion.
Okay. Yeah.
Include fermions is because I'd like to know if you can discuss the real-time interpretation of anomalies which arise in gauge theories that have fermions in them.
Yeah. So of course, in Monte Carlo simulation, you cannot deal with Grassmann variables. So what you have to do is to first integrate the fermionic variables, and then you end up with some fermion determinant, and then which is written in terms of bosonic variables. So after that, you can use the same technique. So of course, there's no potential problem in dealing with fermions, but the computational cost will be much larger, as is always the case with Monte Carlo simulations. So yeah, in our simulation, the Monte Carlo simulation time is proportional to the system size, but if you include fermions, that might be larger than that, and unfortunately. But of course, when we study, well, for instance, finite density QCD or IKKT model, we really have to include fermions. That is absolutely crucial. So in the end, we are aiming to do that.
Thank you.
Yeah, I have one question. The reweighting is likely to be a problem if the phase is large.
Yeah, okay. So you're talking.
You're aiming for it constant, but being large could be a real problem.
Yeah, so when you increase the system size, typically the fluctuation of the phase grows with the system size linearly. But the good thing about this Lefschetz thimble approach is that you have to increase the flow time tau, and then typically the fluctuation of the phase becomes smaller exponentially. So the flow time tau just increase with the system size logarithmically, very slowly. So yeah, so that kind of problem can be handled very nicely in this method. That is the advantage.
The probability becomes small because the real part is getting large.
Yeah, the real part is getting large, so more and more restricted region on the real axis will contribute to the path integral as you increase the flow time. And that way, the fluctuation becomes smaller and smaller, and that will never cause a problem.
Very nice. Thank you. I think there are no other questions, and we should move on to the next speaker.
Okay, thank you.
You are here.
Yes, okay. Can you hear me? Wow. Yes.
Okay, so our next speaker is Mitsuaki Hirasawa,
Yes.
and he's going to tell us about the emergence of expanding space-time in a novel large emitter Lorentzian type 2b. Yeah, girl.
Thank you very much for the introduction. And I would like to also thank the organizer giving me this opportunity to talk about our recent work. Today, I will talk about the Lorentzian type 2b matrix model. Is that? This talk is based on this collaboration. So type 2b matrix model was proposed by these 4 people. And this model is sometimes called as the IKKT matrix model, named after these authors. And there are some related talks at this conference. And this is a partition function and the action of this model. Here, A, mid, psi are n by n Hermitian matrices. The indices mu runs from 0 to 9, and alpha runs from 1 to 16. And this C and gamma is charge conjugate matrices, matrix and gamma matrices after wide projection in 10 dimensions. This model is a promising candidate for non-perturbative formulation of superstring theory. Yes? Sorry. Can you hear me? Sorry. Can you hear me? Or okay, I will. So, sorry. So this model is a promising candidate for non-perturbative formulation of superstring theory. There is some evidence supporting this statement. One is this model can be regarded as a matrix regularization of the worldsheet action. And in this model, the interaction of deep range can be reproduced properly. And the string field Hamiltonian can be derived from Schwinger-Dyson equation for the Wilson loop operator. And this model has n equal to supersymmetry. This is the maximal supersymmetry in 10 dimensions. So this is the evidence for the fact that this model has included gravity. And here, according to this action, the space-time does not exist a priori, and geometry emerges from matrix degrees of freedom. In this supersymmetric algebra, the translation corresponds to the shift of this matrices A mu. Therefore, the eigenvalues A mu are identified as the space-time coordinate. And this model has SO 9,1 Lorentz symmetry. This is a plan of my talk. In section 2, I will explain about the relation between the Euclidean and the Lorentzian model. Then I will explain the regularization of the Lorentzian model. In section 4, I explain how to simulate this model. Then I will show the result and summarize my talk. Next, I will explain the relation between the Euclidean and the Lorentzian model. This partition function is obtained by integration of fermionic degrees of freedom, psi and psi bar. Here, this is a Pfaffian of the Dirac operator. And here we consider the weak rotation in this model. We consider the weak rotation both on the world sheet and in the target space simultaneously. And this U is the parameter for weak rotation. And this phase factor is related to the world on the world. Sorry, this is related to the weak rotation on the world sheet, and this phase factor related to the weak rotation in the target space. And U is equal to 0 case. The model is the Lorentzian model. And U equal 1 case, the model is Euclidean model. This weak rotation is equivalent to the following contour deformation about the matrices A mu. And Cauchy's theorem tells us that this kind of observable is independent of the parameter U. So therefore, the Euclidean model and Lorentzian model are equivalent. So this is a numerical confirmation of the equivalence using complex range one method. I will explain this method later. On the left figure, we plot the trace of A0 squared. This point corresponds to the left-hand side, and this point corresponds to the only this part, and the phase is the same as expected by this equation. And this right figure is trace of AI squared. So also the phase is the same as predicted by this relation. So that we found that the Euclidean model and Lorentzian model are equivalent. So therefore, first I will explain the previous work on Euclidean type 2B matrix model. In Euclidean case, a Pfaffian of Dirac operator is complex value. And if one finds the phase of this Pfaffian, then SSB of SO10 spatial symmetry does not occur. Therefore, the phase of Pfaffian plays an important role. About 10 years ago, they studied this model perturbatively using Gaussian expansion analysis. In this box, they calculated the free energy for SOD symmetric vacuum in this model. And this is the free energy against the D. And at D equals 3, the free energy has take minimum value. So perturbatively, the SO spontaneous symmetry from SO10 to SO3 is predicted in this work. And recently, in this work, they studied the Euclidean model non-perturbatively. So, as I said, the Pfaffian is complex valued in this model. There is a sign problem. So the conventional Monte Carlo methods are not applicable. Therefore, they use the complex random method to overcome this problem. Then they obtain the spontaneous symmetry breaking from SO10 symmetry to SO3 observed. So instead of SO4 symmetry. So therefore, the relation between the emergent this space and our universe is not clear. So next, I will explain the regulation of the Lorentzian model. So before that, I will explain the previous work on the Lorentzian type 2B matrix model. So, in this work, they calculate the classical solution of Lorentzian type 2B matrix model numerically. They obtain the classical solution by solving this equation of motion. The solution of this equation of motion is exhausted by diagonal matrices, and there is no strong reason for the emergence of expanding space. So therefore, they introduce an additional term to obtain non-trivial solution. This is an additional term, and if this parameter gamma is larger than 0, I mean gamma is a positive case, the typical solution has expanding space. Also, its dimensionality is not fixed. And this is the 3+1 dimensional solution. And here, the dimensionality is chosen by hand. Here, the extent of space is plotted against time. Because this model, since this model has this symmetry, I mean, this model is symmetric under the replace A0 to minus A0. So this result is symmetric against t equals 0. and positive time region, the space expands. So in order to, I will explain how to regularize that model, Lorentzian model. In order to obtain a large limit equivalent to the Euclidean model, we add this Lorentz invariant mass term to the action. This is the mass term, and gamma is the mass parameter. The motivation for this extra mass term comes from the previous works on classical solution. And we consider taking this parameter gamma to zero limit from positive side after taking large n limit. And we will see that this gamma can be also interpreted as an infrared regulator for expanding space-time. I will explain this later. So this is a partition function. Here, minus it. This action is defined by I times SB, a bosonic part of the action, plus S gamma. This is a Lorentzian invariant mass term. Here, we consider contour deformation. By using the contour deformation, we obtain this action. So here, the phase for this term and this term, this term comes from the bosonic part of the action. This real part of this phase is positive for this region. U is larger than 0 and small or equal, smaller or equal or smaller than 1. However, the phase for the last two terms, this term comes from the Lorentz invariant mass term. The real part of phase is negative for this region. So therefore, the action is unbounded for this region. So one cannot define the model by contour deformation anymore. So in other words, the corresponding Euclidean model is ill-defined. So we predict that we obtain the result equivalent to the Euclidean model. I showed before. So I will explain how to simulate this model. So first of all, I will explain the setup. In the simulation, we choose an SUN basis, which diagonalizes A0 and by this order. And since this model has sign problem, this sign problem comes from this phase factor. So this phase factor is complex. So then we cannot regard this Boltzmann weight as a probability. Therefore, the conventional Monte Carlo methods are not applicable. This problem is called time problem. So we use complex Lorentzian method to overcome this problem. So in complex Lorentzian method, in order to realize the ordering, we then ordering of eigenvalues of A0. We use the change of variable. Here, we use tau, and tau is real value originally, and we consider this tau is dynamical variable. And in this complex Boltzmann method, in order to take care of the complex Boltzmann way, we complexify the variable. So we replace AI from Hermitian matrices to general matrices, and tau becomes real from real to complex value. And this is the complex Lorentzian equation. So in the simulation, we update this dynamical variable by using this complex Lorentzian equation. Here, eta is Gaussian noise. And it is known that in the complex Lorentzian method, does not always give the correct result. Sometimes the method to give us a wrong result, which problem is called wrong convergence. Fortunately, there is a criterion for the correct convergence. The criterion says that the drift histogram falls off exponentially or faster with magnitude of the drift term. So this is a schematic picture of the probability distribution of the drift term. In this red cases, the probability distribution falls off quickly. In this case, the obtained result is justified. On the other hand, this blue case, the drift histogram has power law tail. In this case, the obtained result is not justified. So one of the causes of wrong convergence is the singular drift term, a singular drift problem. This is a problem that if the operator has near zero eigenvalues, the drift term has a very large value, then the criterion is not satisfied. In order to avoid this problem, we add this fermionic mass term. Here, MF is a fermionic mass parameter, and in the study of in the Euclidean studies, they use the same mass term. And at MF equal infinity, that this matrix is side decoupled from the A mu. Therefore, the at MF equal infinity corresponds to the fermion quenched model. So, in order to see the effect of Suzy, we need to make MF to zero limit, limit extrapolation eventually. And we use another technique. We perform this following procedure at each Lagrangian step for stabilization. A similar technique is used in lattice QCD simulation. And we use very small value of epsilon. So we expect that the effect of epsilon is very small. So I will show the result. First of all, I will show the distribution of alpha. Alpha is the eigenvalue of A0. For various value of gamma, gamma is the parameter for Lorentz.
Sorry.
Okay. Sorry, this is a distribution bar in complex plane. This is gamma equal 1.8, and this is gamma equal 2.6, and this is 4.0. At a smaller value of gamma, for example, gamma equal 1.8 case, this black solid line corresponds to the Euclidean model. So if gamma is small, the result is equivalent to the Euclidean model. However, if gamma is slightly large, then the alpha distribution is different from Euclidean phase. And especially at the both ends, the real time appears. So between this Euclidean phase and real time phase, we expect that there is a first order phase transition. In this work, we focus on this real time phase. So I explain the band diagonal structure. I explain how to extract the time evolution. This is the magnitude of AI, component of AI. Here, I take the average over the dimension, a spatial dimension. And at diagonal part, they take very large value. However, far from the diagonal part, the value almost 0. So there is a band diagonal structure appears in real time phase. So we define the n by n matrices like this. Here n is the this block size, which corresponds to the bandwidth of here. And this, and then I define the time by using the corresponding eigenvalues of A0, like this. And this block matrices A by I represents the state of the universe at time equal to TA. So next, we will see the phase of the space. In order to see the phase of space, we define theta s by using this equation. This is the result for any matrix size equal to 64 and MF equal to 10 and gamma equal to 2.6, which is in Lorentzian, which is in real time phase, and bandwidth is 12. And this black solid line corresponds to the Euclidean model, and this data point result for gamma equal to 2.6 case. So in real time phase and at later time, this phase of the space approaches 0. Therefore, the space becomes real at late time. Next, I will explain the order parameter for spontaneous symmetry breaking of SO9 symmetry. The order parameter is the eigenvalue of moment of inertia tensor, which is defined by this equation. here X is the Hamisha matrices defined by using block matrices. And this procedure is justified at late time because the phase of theta becomes 0 at late time. And SO9 symmetric case, this Tij has 9 eigenvalues. And in SO9 symmetric case, 9 eigenvalues are almost degenerate. On the other hand, SO9 broken phase, the 9 eigenvalues are not degenerate. This is the result. So at t equals 0, all eigenvalues are almost degenerate. On the other hand, at the late time, one of the eigenvalues increases, and the other 8 eigenvalues stays almost 0. Therefore, SSB of SO9 occurs, and this dotted line is a fitted curve for the largest eigenvalues. We fit this eigenvalue by exponential function, and so this 1D space expands exponentially. And this is the result for various value of gamma. We compare gamma equal 4 and gamma equal 2.6. And one-dimensional expansion occurs in both value of gamma. And the extent of time becomes larger at smaller gamma. For example, gamma equal 4 case, the extent is around minus 2.5 to 2.5. However, at smaller gamma case, the extent is minus 3.5 to 3.5. So in the real-time phase, the expansion of the space gets more pronounced as gamma decreases. In this meaning that gamma can be thought as an infrared regulator for the expanding space. So in order to see the effect of fermion, effect of the SUSY, I compare the two values of MF. MF is a fermionic mass term which introduced to avoid the singular drift problem. And MF equal infinity corresponds to the fermionic quenched model, and MF equal 0 corresponds to the supersymmetric case. And MF equal 10 case this is a result for MF equal 10 case, and this is the result for MF equal 5 cases. And so by comparing this result, the expansion is pronounced at smaller MF because the largest value is in MF equal 10 case, largest value is around 10 or less than 10. But at MF equal 5, the value is around 12. So in the real time phase, the expansion of the space gets more pronounced as MF decreases. And in this work, they study the attractive force between the space-time, and they found that the attractive force is weakened by supersymmetric effect. So I will summarize my talk. So we successfully applied the complex Angevin method to the Lorentzian type 2B matrix model. And we found that the equivalence between the Euclidean and the Lorentzian model in the conventional large N limit. And Euclidean model exhibits SSB from SO10 symmetry to SO3 symmetry. And space-time becomes complex, and it has Euclidean signature. In order to obtain the result equivalent to the Euclidean model, we introduced the Lorentzian invariant mass term. And we can see that an expanding real space-time appears at late time as expected from the classical solution of this model. The dimensionality of the expanding space is not fixed at classical level, and it is turned out to be one dimension for MF equal larger than phi. So does the 3D expanding space appears at smaller MF? There is a possible mechanism for the emergence of 3D expanding space. So we can understand our result as the following. So quantum fluctuation is suppressed most when trace of AIAJ square is almost zero. If only one of AI is large and other AI is very small, I mean almost zero, then this situation occurs. Therefore, one expanding space is favored. On the other hand, there is a property of the Pfaffian at MX equals 0. The Pfaffian becomes 0 if there are only two large matrices. This is studied in these works. So therefore, such configuration is excluded by the effect of the Pfaffian. So here, this is the exponential expansion of the space. A0 cannot play any role. And therefore, we expect that the 3D expanding space may be favored the effect of the Pfaffian. Now we are trying to see whether SO9 to SO3 occurs by decreasing MF further. And we expect that 3D expanding space appears for sufficiently small MF. So that's all. Thank you for listening.
Time for questions.
Hi.
Hi. Oh, hi.
Okay. Thank you. I have one comment and one question. So the comment is, it seems to me that the method that you proposed, putting a mass term and some contour rotation, I believe that this is equivalent to putting an sort of an epsilon term to the action which I proposed a few years ago. And this is very important, or very, very good, because this is also what gives you a Feynman propagator. So I think that this this looks very good, and I like that. Now the question would be, so you find this kind of behavior where for very early, okay. So very early and very late times, you seem to get some real space, and in the middle is some kind of a Euclidean-like behavior. Now, it's tempting to interpret this perhaps in terms of a bounce, or maybe bouncing universe in and out state or something like that. Would you, what do you think about that?
It is difficult to determine it is bounce or not, because maybe we need to take n to large limit. I mean, in n to large limit, we can see the more later time behavior. So it is important to see the large, to take large n limit to discuss about the bouncing or not.
Okay, so it's too early. Okay, all right, yeah. Okay.
Thank you.
Thanks.
There were other. I will get you.
I have a question regarding the expansion of one dimension we saw. So in other models like the D0 brain, like BFSS or BMN, there's this flat direction problem, which is related with one eigenvalue escaping to infinity. And this is usually thought of as a pathology of the model. But here you say that this is something physical happening. Are these two related with each other?
Sorry, physical, what? Sorry.
So here you say that you have one dimension growing.
Yes.
But in other matrix models like the BFSS, there is a similar phenomenon, but which one eigenvalue escapes to infinity. And this is thought to be as a pathology. The question is if these two are related to each other. I mean, why here it is physical and in BFSS it is not?
I think in this model, there is, in supersymmetric case, there is no flat region like BFSS model. So
when the matrices commute, it's flat. You have flat directions.
sorry.
When the matrices commute, you have flat directions.
Yes, but by the quantum fluctuation, we can determine we can obtain the stable result in large n limit. And I mean, this one dimension, I expect that this one-dimensional expansion is I mean, lack of the effect of Suzy. And if we take the MF to at a sufficiently small MF, which corresponds to supersymmetric case, then we expect not only one direction, but also, for example, 3D space expand.
Okay, thank you.
So I have a very specific question concerning page 20. I think it's so. Have you studied the dependence of the extent of time on n? So the capital N dependence
Capital N dependence of this phase
of the maximal eigenvalue of time.
Maximum eigenvalue
Of
A?
time, the maximal alpha. See, the question is, does it scale as square root of capital N?
Sorry.
Does it scale as square root of capital N?
We actually we denote the dependence of any dependence of the maximum value of alpha, and maybe yes, we haven't studied the scaling.
Thanks.
Other questions? Actually, I think that we will thank the speaker again and move on to the
Thank
next.
you very much.
Thank you. Here. Hello.
Hello. Okay, this is better. Wonderful. Okay. This looks fine. Okay.
So the next speaker is Juraj Tekel, and he's going to tell us about towards the removal of the striped phase in matrix model, I believe 540.
Thank you very much. we all thank the organizers for invitation, but I think it's really good to stress that this meeting in Corfu is something special, I would say. And I still consider myself a young person, and for us, it's great to have such a robust platform to meet all the names that you usually list on your presentations. So truly, not only for the invitation to give a talk, but also for keeping this up. It's truly appreciated for all the organizers and especially George. Thank you very much. And I'm going to talk about some not that recent and some very recent work with all these people. And my title is rather long, so it serves as an outline of my talk. And the most important part that I want to talk about is hidden here. But since the results that I'm going to mention are rather technical, let me start slowly with explaining parts of the title. So this is something that probably most of you have heard hundreds of times, but yet still, let me start with the fuzzy sphere, which now is 40 years old. And the idea is that when you have a regular sphere, you expand the functions on the regular sphere in spherical harmonics, and to define fine features on the sphere, you need spherical harmonics with large L. And the finer you want to go, the larger L you need. So if you want to lose the ability to describe features under certain length scale, a natural thing to do is to cut off the spherical harmonics beyond certain L. Yes, here you can see as with increasing L, the features that you can describe with that particular spherical harmonics get finer and finer. And when here, instead of infinity, you have some cutoff, you lose the ability to talk about features underneath a certain length scale. And for example, your points cease to exist since you cannot define the series of functions that converges to delta function. Unfortunately, such expressions are not closed under multiplication, simply because if you multiply these two, you obtain function that needs L greater than 1. But the idea is to borrow your product from matrices, and there's a way how you can map the cut off spherical harmonics onto n times n Hermitian matrices, where n is L plus 1. And then you borrow the product from the matrix product, and you come back to the functions. And obviously, since matrix product is not commutative, this new product is going to be non-commutative also. However, you have closed your multiplication, and now you have a nice algebra of functions to work on. And your fuzzy sphere is whatever object this algebra is algebra of functions on. And this object still possesses rotational symmetry, since you can rotate your spherical harmonics in here by arbitrarily small angle. And when you remove the cutoff, you obtain the original sphere. A different way to construct the same object. Sorry about that. You just deform the commutation relation of the generators of the algebra of functions on the sphere in such a way. And when you remember your quantum mechanics, you immediately recognize the commutation relations of SU2 and the spin S representation. And after some technicalities, you obtain basically the same results as we did before. So the result and the short distance structure emerges here due to the the quantum mechanics like uncertainty of measurements of different coordinates. And you can play the same game similarly for plane in 2 dimensions, either by zooming on the north pole of the sphere, or simply by starting with such a deformed product between the functions on a plane. And either way, you obtain a space where you have deformed the smooth sphere into something that has a discrete structure. The underlining feature of the space is matrices being your functions. However, the discretization doesn't work in this way because there are no sharp boundaries between the Planck cells that you have created. And therefore, the boundaries are blurred or fuzzy. And I don't know how well this picture works with this projector, but I like to imagine it like this, but the other way around, that the snakes do not swirl where you're not looking, but they actually, on the fuzzy space, they swirl where you are looking, and they swirl, the closer you look, the more the snakes swirl. And this blurs the boundaries between the Planck cells. Okay. Yeah, this is a slide I usually show to people who need to be motivated to work with fuzzy spaces. I don't think this is the case of this audience. However, obviously for what we have already heard here, the fact that fuzzy spaces arise as various solutions in various matrix models defining the string theories is probably the most important motivation. However, also fuzzy spaces can be thought of as toy models of spaces with quantum structure, which is expected to arise in quantum theories of gravity. So one can try to do physics on fuzzy spaces and see what comes up. And yeah, I myself definitely have gone to the point where when somebody says physics, I imagine 5-4 theory instead of falling rocks and things like that. So let's do field theory, and I don't think I'm going to spoil the story for anyone when I say that things go rather bumpy very soon. So you write your naive action for 5-4 theory. You define your theory with the correlation, functional integral and correlation functions, and you list your commutative to non-commutative dictionary and translate this action to a naive formulation of an action on the fuzzy sphere. And I'm going to use words fuzzy and non-commutative rather interchangeably, even though usually when people talk about fuzzy spaces, they talk about non-commutative spaces that are compact, therefore have finite dimensional algebra of functions, i.e. matrices, and non-commutative spaces are usually referred to as the infinite plane and spaces like this. Excuse me if I'm going to be rather inconsistent in that. I guess we're going to find our way around that. So you write down the action and you compute your correlation functions, and there's plenty of literature on that. Bal has mentioned their book, which is probably or was probably the starting point for all this for many of us. And as I mentioned, when you try to compute things, you come up with UVR mixing, which I like to imagine as in the following way. There is some kind of limit on how small your quantum fluctuation can be. So if somewhere there, a quantum fluctuation which is very located in this direction occurs, then due to the uncertainty principle, the fluctuation needs to be extended in the opposite direction quite far. Yeah, because it was stretched in this direction, therefore it was squeezed in this direction, therefore it needs to be stretched in this direction. Therefore, quantum fluctuations somewhere there do affect the physics in here, which is exactly what you don't want to happen if you want to renormalize your theory. You need to to have the scales separated, and the UV physics, the short distance physics there, has long distance consequences. And technically, when you compute the diagrams, this arises as a difference between planar and non-planar diagram. This is quite straightforwardly seen in the matrix model, in the matrix formulation of the phi-4 vertex, where if you contract the legs in these two ways, you obtain different results. And I'm writing this explicitly here just because this expression is going to pop up again in this presentation. And I'm not sure how well you can see the difference between this color and this color. This is supposed to be red and this is supposed to be black. The important point is that this expression depends on the external momentum. And so when you compute the one loop effective action of the phi-4 theory, you obtain terms that are not there in the commutative limit, in the commutative theory. That would be okay. The problem is that these terms do not disappear in the commutative limit. So when you start with a non-commutative theory, you write down your one loop effective action, and you do the commutative limit, you obtain something different than you would have obtained if you computed on a commutative space from the very beginning. And in the fuzzy sphere case, there's no divergence, so this is referred to as non-commutative anomaly. But this is the important point, that simply the physics remembers where it came from. The space forgets its fuzzy origin, but the physics remembers. And on a plane, you get full-blown divergences, because this diagram here, when you calculate the diagram, due to this oscillation, you obtain an effective cutoff, even when you send your momentum cutoff to infinity. However, for 0p, this cutoff diverges, and this diagram diverges for 0p. And the problem is, when you start the chain diagrams like this, and you would have put a non-local loop on this loop here, sorry, non-planar loop on this loop here, your theory just starts doing strange things. And the bottom line is that naive formulations of non-commutative field theories are not well behaved in the commutative limit. In the commutative limit, they don't give you anything that you can work with. The theory is not renormalizable, and it has different spontaneous symmetry breaking patterns. Now, no matter how many times I talk about this last thing, when I submit my presentation, I just very nervously quadruple check whether this is written with single or double P. And so this is the striped phase. And in usual theories, Higgs mechanism, you obtain two different phases of the theory. When the potential is not deep enough, the theory oscillates around the false vacuum at 0. But when the potential is deep enough, the quantum fluctuations are not large enough, and the theory falls down into the true vacuum of the potential. Now, this has been established qualitatively quite some time ago, and the actual results for the transition line are more recent from numerical calculations. When you do this on fuzzy spaces, due to the non-locality of the theory, different things start to happen. And this has been established computationally and also numerically quite well now. And I refer to this Marcos review paper from Corfu meeting 7 years ago. And this is what you obtain. The field does not, there's a regime where the field does not oscillate around one value in the whole space, but stripes of oscillation around positive and negative minimum of the potential occurs. So the phase diagram that you obtain looks like this, where apart from the two usual phases that you have in your commutative theory, you have a third non-local striped phase where the field oscillates around both minima of the potential. Yeah, around one minimum in some parts of the space and around the other minimum in the different part of the space. So, and now we want to describe this somehow in an analytic fashion, and the way to go is matrix models, because the fields are matrices, the correlation functions are path integrals, which are matrix integrals. So you are working in a matrix model. Now, general matrix model is an ensemble of random matrices. And for us, the important case is Hermitian matrices, which usually when you look into literature, something like this is considered, because this is quite simple. You can diagonalize the matrix, look at the eigenvalues of the matrix, and see what happens. So for such a potential, when R is positive, you obtain eigenvalue distribution that is symmetric around 0. When you take R that's negative but not too negative, you still have distribution that's centered around 0 value and is supported on one single interval. However, when you go beyond certain value of R, the interval splits, because the eigenvalues separate into two symmetric intervals, and you obtain something that's called two-cut solution, opposing the one-cut solution here. And if the potential wells are deep enough, the model also has an asymmetric solution, where all the eigenvalues are in one of the minima, and for the simple models that I have shown you in the couple of slides ago, this solution is never realized, because due to quantum tunneling of the eigenvalues in between the minima, the eigenvalues always end up in the blue solution rather than a red solution, but the solution exists nonetheless. And you probably have guessed by now that this solution corresponds to the broken phase of the commutative theory. This solution corresponds to the unbroken phase of the commutative theory, and this solution corresponds to the non-commutative striped non-local phase of the non-commutative field theories. And now the question is, what happens with the kinetic term? Yeah, recall that there, apart from the potential term for the fuzzy field theory, there was the kinetic term, and you need to compute things you need to compute such integrals when you want to compute your correlation functions. And the technical problem is that the diagonalization of the matrix doesn't work anymore, because this integral over the angular degrees of the matrix is not trivial anymore. And now you need to roll up your sleeves and try to do something, and many people here have spent substantial time doing that. And the way we have done this goes back to Harold's observation that for G equal to 0, the kinetic term basically just rescales the solution that was there without the kinetic term. And then Alexios realized that there's a way to describe this, and you can introduce the asymmetry. And I present to you the model that I have spent a lot of time investigating in later part together with Maria Shubiakova. And long story short, this is the result. This is the phase diagram of such a matrix model. And I want to point to very nice similarity with these two things. And the thing that I want to stress is that in the matrix model description, this phase is difficult to get. Yeah, matrix models naturally have this solution and this solution. The difficult part about these diagrams was to establish that this solution is there and is stable, is preferred to this solution. So this is the diagram of an approximation of the model on the fuzzy sphere. And similar things happen on the non-commutative plane. For example, as I mentioned, you can zoom on the north pole of the fuzzy sphere, and essentially the same thing happens on the non-commutative plane. So, and now let me get to the removal of the striped face, because the striped face was conjectured and is understood as a consequence of the UV-IR mixing because of the non-locality of the theory. Yeah, the non-local thing. And I perhaps have forgotten to stress that this diagram is in the large n limit of the matrix model, therefore in the commutative limit of the theory. And there it is, the striped face still exists even in the large n limit. So this is naturally linked to the UV-IR mixing, where the UV-IR mixing introduces terms that survive the commutative limit. So, and now the idea is that if you manage to formulate a modified theory on the fuzzy space, which does not have the problem with UV-IR mixing, this theory, and you look at the phase diagram of that theory, you shouldn't see the striped face, because the striped face is related to the UV-IR problems. And for the fuzzy sphere, such a theory was formulated by Brian, Denjo, and Peter. And it modifies the kinetic term of the theory. And it essentially just by force removes whatever problematic was in the theory. Yeah, and here you can see a very similar expression as you saw where I showed you when I showed you the UV-IR mixing calculation for the fuzzy sphere. So literally this modified kinetic term just takes all the problematic things in the theory and just sweeps it under the rug. And Denjo and Christian have suggested that this is obviously a very complicated thing to look at, but to start, why don't we look at expansion of this this modified kinetic term in terms of the matrix Laplacian on the fuzzy sphere. So we looked at matrix models with modified kinetic terms like this, where this Q is related to this A and this Q2 is related to this B. It's just that there's a factor of G here, so there needs to be factor of G here. Those are technicalities. So I present to you the phase diagram of that modified model. First, just the first order in the matrix Laplacian, and you can see that the transition line that was originally here has shifted to the right, and therefore the region where the problematic phase existed shrank, and so this is what I mean by towards removing it. And when you introduce the parameter B, you can see that for positive B's the region shrinks even more. And here you can see that the removal happens in a funny way, that the region doesn't just completely disappear, but the region recedes, and it recedes in a way that it recedes more for larger R's, and here close to the origin, it just, you know, takes its time, I would say. But nonetheless, introducing such modification to the kinetic term does at least partially what we would expect it to do. It removes, or it starts to remove, the problematic striped phase from the phase diagram. So we claim that this is, it's not really a proof, but it is another evidence towards establishing the relation between the UV-Ra mixing and the striped phase, because a theory that has less UV-Ra mixing has less of the striped phase. And another model that is free of the UV-Ra mixing was formulated by Grosse and Vulkanar and then studied by many other people, including Harald and Reimar in 2000s. I don't think you call these zeros. Yeah, 2000s. And the point is to, again, to modify the kinetic term. Again, you introduce a theory that is different from your naive version of the non-commutative theory. It modifies the kinetic term. It's quadratic in the fields, and it does things that help to remove the UV-Ra mixing. And establish the renormalization. The mechanism here is a little different than it was for the case of the fuzzy sphere. This term introduces Langman-Szabo duality in between the small and large distances. So it fixes the problem of the two length scales being different. Again, somehow putting them together and us being able to do the renormalization procedure. The important thing is that for us, the important thing is that you can formulate this model on the non-commutative plane as a finite dimensional matrix model, which was done by Buric and Volganand in 2010. And the idea is that in 2 dimensions, again, if you remember your quantum mechanics, you can satisfy such a commutation relation basically by creation and annihilation operators with some eyes. And what you do is you truncate the matrices to a finite size. The commutator is no longer the same as it was before. There's some Z matrix, which is diagonal and almost all zeros. So this matrix model with X, Y, and Z by its own isn't the Grosse-Vulkanar model, but we recover the Grosse-Vulkanar model in the large n limit, or we can say that we force the regime of the model on the Z equals 0 condition, and we try what happens there. Then the kinetic term becomes this, because as we are quite used to, the derivatives are commutators with the coordinate matrices. The difficult part is to translate the harmonic potential term, which, again, this is work by Buric and Volganand from 2010, becomes this. And then when you take your Z equal to 0 case, you find out that my matrix R is a diagonal matrix with almost all eigenvalues being separated by a constant, therefore harmonic potential, which is a check that this truly has something to do with this. And it has an interesting interpretation that for us isn't that important, but I wanted to mention that this R is basically the curvature of of this space. So the field couples to this curvature, and that thing helps to alleviate the UVR problem. So we are left with this n times n Hermitian matrix model, where, just to keep you alert, I have completely changed the notation of the parameters. Especially, I have changed the sign here. So positive G2 now means the wells of the phi-4 potential exist. And our colleagues in Belgrade have done last year some numerical simulations of this model. And they did observe that this is CR equal to 0 case. And the interpretation of the lines is a little different in what I've shown you, but I think you can follow the contours of the two transitions and the third transition here. And when CR is non-zero, there is shift of this diagram upwards that in the numerical simulation was observed to be proportional to CR. And I remind you that, okay, in their notation, GR was denoted as CR. So this is the shift due to the curvature term in the model. And what we, with Samuel and the Belgrade bunch, have done recently was to consider only the curvature term. Yeah, for now, let's forget about the kinetic term, and let's see what the curvature term does. So basically, we need to compute such integrals, and there is a way to compute this integral exactly, Harish-Chandra-Itkinson-Zuber integral. However, the integral itself is not easy to use the result in your matrix model machinery. So what we have done is we have taken the Harish-Chandra-Itkinson-Zuber formula and we have expanded it in GR up to fourth order. And to check that, you can do also the things the other way around. You can first expand this in GR and then do the integrals by some character expansion, and you obtain the same result, obviously. And this is the matrix model that this translates to up to GR to the fourth. And there are, okay, this is a multi-trace matrix model. Up to the first order in GR, you get only a shift in G2. Up to the second order, you get shift in G4 and some multi-trace term. But still, up to order GR squared, you get a model that can be handled completely analytically. And you get such a phase diagram where I remind you that this diagram is the other way around. Yeah, it's upside down. So this is the original phase transition of the pure matrix model. Here under the line, we have the one-cut solution, the unbroken phase of the field theory, if you wish, and above the line we have the two-cut solution, the strange non-local non-commutative solution. And you can see that as you increase GR, this line moves up, and therefore the region where the striped phase exists again recedes. It recedes in a different way than it did before, but it recedes nevertheless. And if you wondered what this means, this is a region where the second order approximation in GR is no longer to be trusted. And if you go to higher order in G, you now obtain a matrix model that is not a simple quartic model. So this is not that straightforward to analyze. You need to do some technical, either perturbative or numerical solutions. Anyway, this is a diagram for some small value of GR, and the green line is a numerical transition line of the model, and the orange line is analytic transition line up to GR to the 4th power. And the blue line is the transition line up to the 1st order in GR. Yeah, so I realize it's quite close to the coffee break, so I perhaps will repeat that once more and in much simpler way. This is 1st order in GR, and this is 4th order in GR. So this shows you that when you include more terms in GR, the phase transition line moves even further away from the original transition line, and you get the striped phase recedes even more than it did before. Wonderful. The last thing we did is we checked numerically the partially full model. So the dots that you will see on the diagram are dots for the numerical investigation of this model without doing this expansion. So we took this term completely, but we still disregarded the kinetic term. And as you can see that the transition points were quite on point with the transition line. And here where our GR to the 4th approximation is not working anymore, you can see that the transition line, numerical transition line, continues nicely to some finite shift at 0 G4.
What are the different?
That's a great question. Those are, yeah. So obviously, Denjo with his trained eye has immediately seen that there are 3 dots for the same value of G4. These 3 dots are 3 different determinations of the phase transition line. One is specific heat, the other uses eigenvalues, and the third one uses eigenvalue distribution in a little different way. Now, they are different. These are finite n, so they give a little different phase transition point, but they all converge to the same in large n limit. So the points represent a different method to determine the phase transition numerically, which give different finite n results, but in the large n limit, they tend to agree.
What value of n have you plotted?
I believe this is 24 or 30, 24 or 36. 24. Okay. So I want you to, or I want you, that's a little aggressive, isn't it? I would be really happy if you could remember these 3 points from my presentation. If you want to deal with fuzzy or non-commutative field theories, matrix models are the way to go. You very soon run into UVR mixing problems, which in our settings exhibited as a strange phase in the spontaneous symmetry breaking pattern of the phi-4 theory. And there's a way to alleviate this problem. And when you do that, the matrix models seem to agree that the striped phase is removed together with the UVR mixing. And obviously, an interesting thing to do would be to include the kinetic term into the analytic considerations that we have done. Then it would be interesting to investigate the gauge model that was inspired by the Gross and Wolkenar model, and which also was hoped to be free of the UVR mixing, but turns out that that model still includes the UVR mixing. The UVR mixing is not removed, and it would be interesting to see how this translates into the phase diagram of the theory and the striped phase, and obviously some non-perturbative treatment of the curvature term, perhaps in a similar fashion that we did with Maria for fuzzy sphere would be interesting to do. And with that, I thank you for your attention.
Questions? Section is in quick.
I have a few comments. The first one is historical, which I feel somewhat strongly about. I was the first person to show that there is UV-IR mixing for 5-4 theory on the fuzzy sphere, S2. And what I showed is that that because of UV-IR mixing, it's not possible to write down the renormalization group equation. I think that soon after that, there was a paper that you quoted by Harold. And very soon after that was the paper by Brian, Denjo, and Peter, where they showed that if you do a non-local redefinition of the field, the UV-IR mixing problem goes away. And a similar work, a little bit later, was done by the person sitting next to me, Patrizia and her collaborators, who showed it, showed it in an alternative way. But again, the point stands, which is that if you do a non-local redefinition of the field, UV-IR mixing goes away. And talking of non-local redefinitions, I also want to point out that very closely related work that we did with Sasha Pinzul and Bal, that if you take a quantum field theory and make a non-local redefinition of the field, then such a quantum field theory, 5-4 theory, for instance, defined on the Moyal plane, shows no UV-IR mixing whatsoever. So I think that it's sort of important for us to know for everyone to know these points. And
thank you.
These are the comments I have.
Okay, Patrizia.
Thank you.
I get you.
Well, my comment was a little bit similar in the sense that in 2013 with Jean-Christophe Wallet, we studied what is called now the fuzzy onion. We called it R3 lambda. And we didn't use fuzzy harmonics. We used the matrix basis. We kept the kinetic term. And at one loop, there is no UV-IR mixing actually. So maybe you could have a look at it. Okay.
Thank you.
And after that, we have John online, and then I'll get to him.
Let me first remember what happened in the Moyal plane and the paper you quoted by Susskind, Minwala, and the third party. Where they claimed that the Moyal plane formulation was inconsistent because of UV-IR mixing and in fact causality in that paper. Okay? It was proved it was actually shown much before that by the Rome group, namely Dorothea Barnes, Fredenhagen, and Sergio Doppler, that the function there is no reflection positivity is not fulfilled in the Euclidean formulation of the Moyal plane. So anyone doing calculations by that is simply doing wrong things. So they calculated things in Minkowski space, and they found out that the time order product, and inside that you have the fields, there is a star product, and it cannot be pulled out of the time order product. So the Moyal plane formulation in the Euclidean space is simply wrong. Okay, and they withdrew the paper, by the way. The paper you mentioned was withdrawn later. Okay, so
you mean this one?
That paper was withdrawn. Okay, it was never published. In the case of the fuzzy sphere, I don't remember what happened in the with reflection positivity. I don't remember studying it myself. Maybe Sachin remembers. And the S2 that comes in the fuzzy sphere is a space-time or space. I am not exactly remembering. You can do it in 2+1, do it for space. There is no problem in the functional integral. But if you do it as space-time 1 + 1, then I don't quite know how to check reflection positivity. It is absolutely important to check reflection positivity. I don't remember anyone doing that in Euclidean function integral in 1 + 1 for the fuzzy sphere. So there is maybe something lacking there. Without reflection positivity, the whole thing is wrong. The functional integral is not the solution of everything. It may be easy, but it can lead to wrong results.
Okay.
This is what I remember. My memory regarding fuzzy sphere is not, regarding Euclidean functional integrals, is not precise. Okay? I do remember Sachin doing that when we were in Mexico. It happened. This whole event happened, and I don't know what subsequently happened. Okay.
Thank you.
Yes, Jun has some.
Yeah, let me ask you about the purpose of removing the stripe phase. So even if you have some additional terms, I think you still have star products everywhere in your Lagrangian. So I believe that non-locality should exist always. So are you planning to remove even the non-locality, or you just want to remove the stripe phase, but not really the non-locality?
Well, to answer your question, that the non-locality is removed in the Lorentzian limit. So, and these considerations are in the Lorentzian limit. So the matrix is here. Yeah, the matrix is where the star product is basically the matrix product in between the two matrices becomes the usual product in the Lorentzian limit. So in the Lorentzian limit, the non-locality is removed, and we try to remove the striped face by such extra terms.
So are you saying that the field theory you obtain in this way is basically equivalent to commutative field theories?
Well, what I'm claiming is that when you take such a matrix model, then the striped face is removed. The question whether it's completely removed depends on what happens when you take GR to all orders and you include the kinetic term. So I'm not really sure what happens there.
Yeah, of course, the stripe phase is a consequence of UVR mixing, but the absence of stripe phase does not really mean the absence of the UVR mixing. So that's what I'm a bit confused about. So you don't have any definite answer to that?
No, I don't have definite answer to the claim that no striped phase means no UVR mixing, but clearly less UVR mixing means less striped phase.
Yeah, that is true. Yeah. Okay. Okay. Thank you.
So it's like half question, half comment, actually. So I was always confused about fuzzy sphere in the following sense that it seems to me a little bit illegal to ask some kind of global topological questions. Why? Because I mean, fuzzy sphere is essentially some finite matrix model, and you recover the commutative one by some kind of inductive limit. So K theories are completely different for two. So meaning that for any finite matrix algebra, K theory, the second one, the first one actually, is completely trivial. And K theory is stable under inductive limits, so it will be trivial in the limit. While for the commutative sphere, it's not trivial. And K theory controls essentially the global structure of bundles over your space. I mean, so the point is that I've always felt that, like, I mean, so in what sense the fuzzy sphere converges to a sphere? Actually, in kind of like Gromov-Hausdorff sense, in the metric sense. So that was shown by Riffel. I mean, so metrically it does converge. So, but it's more local in a sense. I mean, so that's why I think that's why when we take the limits, like n goes to infinity limit, we start looking like on the level of action or some local expressions that it does look more and more commutative. But the moment you start asking some more global questions, I think you should expect kind of discrepancy. I mean, like 3 going to 2 cannot do continuously. So just question or comment if you know some comments about
No, I don't have comment beyond thank you, and I will think about that.
Maybe I can answer. We constructed all of the equivariant vector bundles on the fuzzy sphere and higher CPN manifolds, and so the K theory is under control in that sense, in that you know how to construct all of the equivariant vector bundles. They are cut off but there is a well-defined limit in which you get it. That's a slightly different question to what he's addressing here. I had one comment on the motivation for removing the our motivation for removing it was to use the fuzzy sphere and its analogues as a regulator of quantum field theory. And for example, one would like to understand if you could show your phase diagram. If this section connected to the origin, one would have expected that the transition as one crosses that to be in the Ising universality class. But with the UVIR mixing, or with that additional phase, it wouldn't be. And our motivation for introducing that counter term was to restore that. And one can see that all of the diagrams that are divergent are removed by that counter term. So that was our argument. That was the motivation.
Thank you.
And Harold.
Okay, thank you. So I would also like to make some comments here. I also have some strong feelings about, in particular, about some of the comments which were raised. So to address, I think the fundamental problem with all these considerations is one has to be very careful to distinguish the infrared regime of functions of field theory and so on from the ultraviolet regime. Now, all the questions concerning topology and classical limits and so on, they can only be addressed in the infrared regime, and then there is no question if something is a sphere or anything else is completely clear. On the other hand, when you start to talk about quantum field theory, which is well defined in a matrix model framework and different from twisted and other frameworks. Now, in the quantum regime, you see that the dominant degrees of freedom are completely non-local. It has nothing to do with a local field theory. It's completely non-local string-like thing. It's really a string-like theory. And this is the origin of UVR mixing. And this is why all these theories are completely non-local and will never recover the classical theory, except maybe in some maximally supersymmetric case. So I think that this very often gets lost, and it was implicit, of course, in the talk, but that's the reason why one really has to distinguish these regimes. So there is the only chance to make contact with anything classical is only in infrared regime, and then there is very clear what is geometry and so on and so forth. But the quantum behavior will be completely different. It's always non-local in these cases. And look at string states. This makes it completely manifest, in my opinion. Just okay.
Okay. We're going to miss coffee unless we do that. So I'm going to cut it off.
Just I wanted to add that, if you are in the usual case in the continuum, there is the Higgs particle there. So it's physics. It goes there and distinguishes from other cases.
And Paul wants to come back in with one very quick comment. And we can move to coffee then.
Sasha's comment in your reply. Actually, in the paper with Sachin and I think Sechkin, we looked at the fuzzy sphere case, but we did not use functional limits. We constructed a projective module on which the Dirac operator can act, and showed that which is appropriate for instantons, and showed that the Dirac operator had a correct number of zero modes. That is the left chiral. So, as he pointed out, they were following a method which they elaborated, coming from Grosep, Klimchik, and Brezhnev, if I remember correctly. Secondly, I want to ask who checked reflection positivity in functional letters. Otherwise, I don't think it means meaningful to talk about UVIR mixing. I simply don't think it is meaningful. This may not correspond to any field theory or any positive Hilbert space.
This is true. No, I would say that the model is not reflection positive.
then it is not a field theory. It's not a physical theory.
It is a condensed matter theory. It should still be
No,
in the Ising.
there is no Hilbert space.
We,
You can't, correlation functions are not in a Hilbert space without reflection plausibility. You agree with that? No?
I agree with it. The question is whether one of limits in the end. Anyway, I think we should move to coffee. Right, and thank the speaker again for stimulating a
Thank you.
very strong discussion. We are supposed to
I think 11:45. So could we make it 12 so that everybody? I don't know. All right. Could you please announce that?
We'll resume at 12, just so that there's a reasonable coffee break.
I just wanted to do it for the online participants too. Thank you very much.